Okay. Okay. Mrs. Santi is CEO of Light Progress Group, and a national company specializing in UVC technology for air and water quality. CGUVMP certified and president-elect of the newly established ASHRAE Italy chapter. She leads global business development, technology, communication, and international partnership, and frequently speaks at international conferences on indoor air quality and UVC applications. Ms. Santi, we're waiting your speech.
So good morning, and thank you for this invitation, and it's an honor to be here. I'm going to talk about a real application of ASHRAE 241. ASHRAE 241 didn't just give us a standard, it gave us a mission to quantify the infection risk indoor. But for any standard to succeed and move from a medium into a real messy existing building, it needs to be improved and try to be applied. So the work I'm presenting today was conducted by a research team at HYGEIA2026, my team at Light Progress, and collaboration also with other companies providing smart thermostats and NANCO for the certification of all the team and the people involved. So ASHRAE 241 sets a target, as Professor Buffett explained earlier, better than how I would be able to do. The equivalent clean air flow per person is the target under infection risk management mode. And so that gives building operators flexibility in how to meet this standard. And what we did in our study was to test one of those pathways, germicidal UV technology, in common areas of a single care facility. So we developed tools needed to measure the compliance with ASHRAE 241, and then we tracked what happened to the residents in the building, and the results speaks to three things at once: whether the standard is implementable, whether the math behind it sounds, and whether compliance translates into fewer people getting sick. Those three are the condition for ASHRAE 241 to be broadly adopted. And that is what this study is about. So ASHRAE 241 is built on a simple but powerful idea, not how to deliver clean air, but how much clean air space must deliver per person based on the scope of the building and the facility itself. The number is the equivalent clean air exchange, and that value needs to be multiplied by the occupancy, and that gives you the targets that you need to match. The targets are higher than standard 62, so if we consider standard 62 as a starting point, all the buildings should be doing something to meet the ASHRAE 241 standard. But the critical part is the standard explicitly recognizes that you don't have to meet them with ventilation alone. You can use filters and get credits on a MERV scale. You can use GUV and get credits when it's properly designed. And this flexibility gives engineers a way to choose between a mix that can fit their constraints. And our project focuses on quantifying what these pathways, and specifically GUV, can realistically deliver in an existing facility when major HVAC retrofits aren't feasible. So almost everything that has been published so far about 241 application has been theoretical and modeling studies or engineering analysis. And so there are very little field data about the application of 241. That is the gap that we tried to address. So we took the standard into an actual senior living facility in Minnesota, and we use the risk tool to benchmark existing condition against the equivalent clean air targets. We develop a quantitative method to compute the specific contribution of GUV to get to those clean air exchange, and then we measure what happened. So one question was about the engineering side, and one question was about the human side. This study started with like a reality that every facility manager knows, especially in senior living communities where most of the tenants are under a memory care control because they either have dementia or Alzheimer's, so they don't go out to the facility, they have visitors coming in, and then the staff is dealing with them on a 24-hour basis. So the question when a resident gets sick is, where did he come from? And the second question is, how many people will be sick next week? So these operational questions are the why behind the standard 241, and our job was to provide the how. So we framed our work around two core questions. The engineering question was, can we design a GUV implementation that reaches 241 targets in an existing building without changing the HVAC system? And the human question was, if we reach those targets, do people actually get less sick? So every slide that follows is designed to answer these two main questions. Senior care is a high-stakes environment. There's high density, people inside are more vulnerable, and building design is about comfort and not infection control. An outbreak isn't just a clinical event in a senior care facility, it's an operational crisis that destabilizes staffing and family trust. This is exactly where a performance standard like 241 is most needed, and not just on a risk base, but on a seasonal base. For example, for a common flu season during wintertime. And the reason why I approached this study with the university was because I come from Italy and I've seen what the pandemic did to the elder in our community, and the way that hit us was very hard to forget. So the gap we are helping to close is the lack of empirical field evidence, and operators need to know, can an older building realistically meet this target? What mix of intervention is most effective, and how do we balance the safety with energy and operational reality? So our study wasn't to grade the standard, but to provide data that supports its real-world adoption. Our contribution focused on precision, so field-based assessment in the real rooms with real environment and real people doing their work and living the building, no simulation, and a quantitative method for GUV contribution, treating it as a measurable clean air pathway. We have to remember GUV is pathogen specific, so we needed a pathogen specific approach that respects the biological reality of this infection. And this aligns with the 241 spirits: quantify, compare, and choose the intervention that is the most practical one and close the gap. For those of you who are not aware how the room GUV works, creating a disinfection zone above 2.1 meter and in a way where the air movement, whether if it's natural or mechanical, circulate pathogens into this irradiated zone when viruses and bacteria are inactivated. And the result is a continuous disinfection during occupancy without chemicals waste, without requiring a full HVAC rebuild. It's a passive secondary layer of protection that can be used in room. So targeting specific areas in the building where the probability of contamination is higher. Inside the 241 framework, GUV is a powerful lever because it adds equivalent clean air without moving more outdoor air. For many buildings, increasing ventilation or filtration has mechanical and energy limits. GUV is highly efficient and Department of Energy has confirmed that it can reduce the emission without the energy penalties of a high ventilation strategy, and it makes 241 compliance pragmatic for existing facilities. So reproducibility was the key. The work followed a guidelines that is called ASHRAE GPC37, that is a commissioning guidelines. So the installation was made by a qualified local contractor that went through a certification to be able to do the commissioning, and the analysis was independent, made by Purdue University. We also use real-time CO2 and occupancy monitoring to stay connected to the realities from distance. So this holistic approach creates a workflow that other engineer can replicate. So design, commissioning, quantify, and then evaluate. The site we use as the treatment site included six common spaces, library, memory care, entertainment, community room, and the fitness room. The centralized HVAC used MERV 9 filters as default, and that gets 0 credit under 241 standard. So this meant that our baseline was entirely dependent on the outdoor air. The facility is representative of thousands of existing buildings that now need a path towards 241 performance that is applicable. So for the step one, we characterize the UV field, which might sound very fancy and hard to do, but it's pretty much using IES files, which are common in lighting. And using these IES file, there is a open source 3D tool that is available. It's called Illuminate, where you can put the size of your room, then you put your IES file, and it gives you, by inputting these inputs, it gives you a quantitative estimate of how much UV energy you are delivering in the room. This allows us to connect specific lighting design to measurable clean air credits. So to quantify GUV contribution, we try to connect physics to biology. Pathogens have different sensitivities to UVC. The same UV field generates different outcomes, and so different equivalent air changes for SARS-CoV-2 versus, for example, rhinovirus. We highlight community research is needed for this. So we need standardized aerosol phase and activation data, first of all, because all the values that you see here, the key values, so the resistance of microorganisms to UV is based on water solution. So I think sharing this gap will help us all to improve how we apply the standard using the GUV pathway. Then the third step was to convert the UV effect into equivalent clean airflow in CFM, so it joins ventilation and filtration in the 241 accounting. And then we add it all up and check against the target, getting the results of either pass or fail, and we try to express everything in a single metric, making the compliance calculation transparent and rigorous. Just to give an example, we took the community room here. So you can see the 241 target, the 1000 CFM based on the occupancy of the room declared by the facility. So without changing the amount of people that could actually be together in the room at any time. So the GUV design delivered 1,770 equivalent CFM based on SARS-CoV-2. So if we do a pass or fail, the room surpassed the target, and this quantitative method show where we stand with this room, but then when you go to another room, you can see even if the 600 CFM is pretty much half what we were looking for with the previous room, the gap that was left of 222 CFM was not matched by GUV if you account for different pathogens than SARS-CoV-2. So you can see that every room is different, which is why this room-by-room assessment is vital for GUV implementation, and the fact that the key values are different from pathogen to pathogen. So going back to engineering question, can we design a GUV implementation that is going to achieve ASHRAE 241 without any HVAC changes? Yes, in this case, it did. The conformance was achieved for SARS-CoV-2 and other UV-sensitive pathogens through the installation of just 11 lighting fixtures in the highest risk common zones without any modification of the HVAC system. For more resistant pathogens, it would not have been sufficient, and a mixed fixture, a layered approach would have been better, and this reinforced what 241 philosophy is, a layered quantifiable strategy to address the risk. So to help 241 mature, we must be explicit about some limitation. The well-mixed assumption is not always matched. CO2 data that we track show that air wasn't always perfectly mixed. Quantifying this error is probably a research priority. The inactivation constant, as I said, we need better aerosol phase data, and the risk model, a pathogen-specific risk tool, will strengthen the targets. Then from the engineering performance to the real world and the health outcomes, we compare our 241 compliant facility with 4 other facilities from the same owner within the same region in the same period of time. And they all look the same, and I went there and I promise you they all look the same. It's the same project that is just copy and paste in different cities around the Minneapolis area. Only our site has GUV and was matching 241, all the other sites weren't. And we wanted to see if tracking the health data from all the tenants, we could measure a difference between the five facilities. And the results were striking. The 241 compliant facility has 6% infection rate, 7 cases of flu during the whole flu season from October to May. The 4 comparison sites ranged between 40% and 41%, and these represent approximately an 80% reduction in illness compared to the highest risk control. So the engineering success aligned with strong health outcomes. So for the human question, do people get less sick? In this case, yes. So the 241 compliant facility was the safest site in the group. And so while field studies are a signal, not a proof, and larger trials are needed, the data is highly encouraging. So encouraging that the owner of the facility decided to install GUV in the rest of the facility they own. So we somehow proved that a properly designed GUV application can reduce the transmission risk exactly where it's needed the most. What are the conclusion of this study? In senior care, air is the infrastructure of care continuity. When air fails, operation fails. This pilot shows that 241 compliance is achievable, and it's practical in existing building. So using these quantitative pathways, we can integrate infection control seamlessly, protecting both operational assets and resident lives. Thank you. If you have any questions.
Any questions? Okay. Thank you, Mrs. Santi. There is one question.
Thank you, Giulia. An excellent study, and one of the very few in the world I've seen where somebody's actually followed engineering controls with clinical outcomes, so congratulate you on that. As you say, it's a pilot study, and it's triggering loads of questions. So you achieved ASHRAE 241.
Yeah.
They say augmenting or topping up, and your solution was to add in genocidal UV.
Yeah.
If somebody had gone to another facility and got to 241 by adding in portable air cleaners and media-based filters, I wonder would they get the same result? And what are we actually looking at here? Is the effectiveness of UV, or is it achieving ASHRAE 241 by any outcome would have the same effect?
This is a great question. So to be clear, we only measured in the study the upper room GUV because there is a way to calculate the fluence and so to quantify what is the the upper room GUV adding as a value in the calculation tool that is provided by ASHRAE 241. We also include portable air cleaners because in some areas of the facility it was practically impossible to install upper room GUV because of aesthetic reason. They had a soffit that wouldn't allow us to put upper room GUV because you wouldn't have interference in the fluence rate, so we use portable cleaner. The problem in the study is we cannot quantify how much the portable air cleaner was adding to the total, equivalent change that you can adding, more layered and different approaches. We also did a studies previous to this one in Australia that is called SAMRI and was made right after COVID, but I think, it took a year and it was made by epidemiologists. So I can tell you that those epidemiologists measure completely different values, so a lower effect, a 12% in reductions in contamination within something similar to what we did. They were using our system as well. There was no fluence calculation. So my suggestion is we should put together epidemiologists and engineers, because when you do a study with epidemiologists and no engineering calculation of what are you doing with your space, you are lacking a part of the equation. If you just use the engineers and you don't have the epidemiologists saying, don't, put a filter or a portable filter here because this room is small and then the patient is going to be close to the doctor, that's never going to fill the gap of closing the calculation and saying, wait, this is how much you should be doing, and this is what's the outcome that you can expect.
That's great. Great study, thank you.
Thank you.
Thank you, Nicholas.